to be here in person at this conference. I think I was last at this one in 2019. Can't quite remember where it was, but anyway, I've only been to Sweden once, so it's a nice opportunity to have a look at this different country. So, just by way of introduction, I have a lot of interest in U-Boot, which is a bootloader for APs, and this talk is not for those of you who are big fans of UEFI, I'm afraid. So, yeah, I already said to Elias to sit at the back with some noise-cancelling headphones or something, but anyway. So just with that, by way of apologies, so just I thought I'd mention that. Part of it's going to be a little bit of a rant, and I could go on for days, but anyway, let's see how we go. So I'm going to talk about the problem of booting and updating firmware and some of the existing solutions. And then I'm going to go on about this VBE thing and some of the strange things about it, or some of the different things about it compared to UEFI, and then what the firmware future may be. One thing I have noticed about Sweden is the water glasses are extremely small. So I might have to go over there and get some more. So here we go. So I'm a bit old school, so I've got my little notes here. So the question is, how should we architect firmware and the OS together in an embedded system? And that's been somewhat simple for a number of years, but it's getting more and more complicated. But what we do want, so far as possible, is simplicity. We want it to be secure. We need to be able to update it in the field. We want it to be as open as possible, open source, but also just open in terms of the way you build it and so on. And we want it to be able to be unbricked no matter what happens, even if we ship a bad update. And some secondary things that are important are to minimize the amount of read-only code. So that's the code that you put on there in the factory and you cannot change without an RMA or something like that. So the less that there is, the more option you have to fix bugs in the field. We want the firmware and the OS to communicate and act as a cohesive whole, not, the firmware does its thing, the OS does its thing, and they can't really, no one knows what's going on. And we want the OS to be able to request things from the firmware. For example, when you boot Linux these days, it likes to have some random numbers. So we'd like to be able to, and various other things. We'd also like the OS to control all the updates. We really don't want the user hacking around with the USB stick or having to go and do some weird special procedure to update the firmware. It really needs to be sort of built in. So with those, and there's many other things on that list, but with those, let's look at some of the existing solutions. So we have Tiana Core UEFI and the UEFI standard and all that sort of thing. Tiana Core itself supports, I think it's about 10 boards, and someone can correct me if they know the number. Okay. Yeah, I think U-Boot's about 1,200. I mean, I looked at this the other day, but I'm not necessarily at the top of tree. But it's really not a shared source tree in that sense, because presumably there's development happening elsewhere. There's also EFI support in U-Boot, which is the EFI loader feature. Now, this is a pretty complex piece of software, and I'm going to talk about that in a minute. There's also, in the U-Boot domain, there's this distro boot script stuff. So this is a set of scripts that will find the device and boot from it and all that sort of thing. They don't do firmware update. But you can do that with things like Mender and so on. And there's a new thing in U-Boot called Standard Boot, which aims to get rid of the scripts and make it part of the basic operation of U-Boot, but it has the same problem. So why not use U-Boot with EFI loader? This is the point where you block your ears. Yes, maybe someone could do it for him. Um, well, I'm sure there'll be some questions at the end, and I'm very looking forward to being challenged over a beer. Anyway, the spec is large, it's very complex, you don't need it all, as earlier said. It's designed for closed source though. I mean, it uses UIDs. UIDs are a way of obfuscating what you're talking about, right? It's effectively a hash of what you're talking about. It makes no sense. It uses dynamic libraries, which makes it harder to get rid of unused code, makes it harder to build, makes it harder to run. It absolutely avoids device tree where possible, and there's lots of battles and workarounds that come from that. It's about 100K of code in U-Boot, and it is a bolt-on implementation, although that is actually improving. It's also incompatible with the existing U-Boot flow that people are familiar with, like bootm and standard boot and so on. And I actually think it's a closed source Trojan horse, because it's got everything you would want if you were doing a closed source solution. It's perfect. You just bolt in your closed source thing, it still boots Linux, everything still works, and you're happy. So that's what it feels like to me. And so that's why I said this was going to be a rant. This is my rant portion of the talk. This is the way I feel about it. So let's just review what are the advantages of open source firmware. And Ermin actually mentioned this very well in the previous talk, so I'm not going to go into any detail on this. But essentially, you know, some of the advantages are there: better quality, more secure. Ermin mentioned control and being able to do fixes quickly, and I think that's a big thing as well. Also a single source tree. So it's not a special thing that's built for your big company because you've got a lot of control. They then have to do a new version of you every time they do other thing. It's not integrated into their source, that kind of thing. So the question for me is, what will things look like in 10 years if we carry on down this path of the UEFication, if you like, of firmware? So the complexity is already high, I think. I think that Linux will say, oh, well, you know, you have to have an EFI environment to boot. In fact, the EFI stub will become requirement of Linux. And I've heard people say that. I'm not saying that it's happened, but that's what I think we'll end up with. And I think at the end, we'll have this very easy way of having everything be private, everything be UEFI and so on, as I said. You know, Tiana is a permissive license. Maybe that's why it doesn't have much board support, because all the development's happening somewhere else. I don't know who's using it, but that's what I wonder. But in terms of open source, it's already a failure. So I think as an industry, we should promote open firmware. I don't just mean open source. I just mean open in general. Open source is obviously part of it for our children. Because what we do today will, you know, our children will end up using. And I pity the poor people if the firmware environment carries on down the way that it is. So that's my pitch. So verified boot for embedded is really just a way to say, okay, don't want to use UEFI. What could we do? And the answer I heard was, well, nothing. I mean, there's a standard UEFI. We just use it. We implement it in open source and we're good. So my answer to that is, really? I mean, how did they come up with that standard? Can we not come up with something else? Can we only have one? Is it just because it's 2,000 pages or 3,000 pages and no one can bear to imagine writing that much stuff? I'm not sure. But I've been coming at it from the other point of view. What if we can't use UEFI or don't want to use UEFI? What would we do? So the approach with VBE is essentially to cover the whole life cycle. It uses device tree as a first-class citizen, so it's obviously more targeted at ARM, RISC-V, and so on. Not to say that you couldn't use it on x86. It's relatively simple, and it's basically builds on the features in U-Boot already. And I'm calling them industry standard just to provoke people because, you know, I think the other thing I hear is, well, UEFI is an industry standard. We have to use it. It's an industry standard. I mean, U-Boot's an industry standard. It's been used for years, for more than a decade, on just about every embedded system you can imagine. So, you know, we shouldn't lightly go away from the features and abilities that U-Boot has. Okay, I'm down to 2/3. So, what does it look like? So this is the simple view of it. We have a piece of the software that starts up the hardware, and then we have this new bit which selects and verifies what it wants to run. So every system has to start up at some point. I suppose I've got a pointer here, right? And then, sorry about you guys on the other side, I've only got one pointer. And we start the hardware, then we come into this thing where we decide what firmware we want to run. Once we've done that, we have a little piece that sets up the DRAM, and then we're into U-Boot, Opti, whatever else needs to be done over here. And the key thing is that this is the read-only portion over here, and this is the read-write portion, meaning it can be updated in the field. So we want to minimize, as I said before, we want to minimize this stuff here, make it as small as possible. So that's essentially the boot flow of the firmware. If you're familiar with U-Boot, the only new thing here is that VPL box, which is a recent addition. Everything else has basically been around for a while. When we look at the operating system boot, this is the piece that UEFI does today. So first of all, you've got to figure out what available boot devices are there. You know, you might have MMC, USB, and whatever. You've got to look through those boot devices and find what I'm calling boot flows. A boot flow is essentially a mechanism of going through, it's time to wake up, mechanism of going through the different boot devices and finding these operating systems that you might want to boot. Once you've done that, you pick one, then you load it, you load the kernel, you load the RAM disk or whatever. And once you've done that, there's this strange little bit called fix up, which is where you actually go and add things into the device tree to pass on to the kernel. And here I'm talking in particular about Linux, but it is used in others as well. So for example, what are the boot args for the kernel, you know, that it wants? You need to be able to pass that along. So that fix-up thing is where VBE comes in, because it actually does quite a lot more work in that little piece, adding in things that the kernel wants, as we'll see in a minute. Oh, and of course, it's probably important that you start the thing, but it's pretty obvious. Okay, so what about the update flow? Well, with VBE, this works with firmware update D, which is a user space daemon. The way it works is you go and find an update. It's key to your particular system or software solution. Once you've done that, it's either firmware or OS. They're both handled in a similar way. You write it to the media. You update the information about the version that you now have. And then at some point you have to reboot, because until you reboot, nothing takes effect. But it can happen in the background. And you can see for the OS, it's similar, basically along the same lines. The firmware update format that I've chosen for this is essentially like a FIT. Now, some of you, I don't know how many of you are familiar with FIT. It's basically a way of putting images in a tree. You have multiple configurations. See, I'm looking after this side now. Multiple configurations here. Here's just one. And it says, okay, the firmware is this and this, these two things. You then go and pick them up from there, from these labels here. So you can put a whole lot of images in there, and then you have multiple configurations. And it's the configurations that are signed. And that signing actually is how you protect yourself. Anyway, so essentially it is really just a normal FIT, but there's some special bits in it, like to say, for example, that This one is designed for SPL. It includes version numbers, so once we apply the update, we know which version of the firmware is now present. So what about the kernel update? Well, it's the same. It uses fit, and you can see the same sort of things. We've got our configurations here and so on. We've got our kernel and our FDT. It doesn't mean that you have to put the kernel in there. In fact, generally, there's a thing called external fit, which means that the actual data is stored somewhere else, or it could even be in its own file. But essentially what we do need is this metadata. And this is what I'm going to talk about in a minute. But this up here is where you say what the operating system wants. The things that it wants you to pass to it in order to work. I'll just briefly talk about scanning for boot flows. So in this case, I mentioned before, we have some boot devices, boot devs I'm calling them, and that's just a list in some sort of order that the user may set. And we actually use the VBE boot meth, which is a boot method, to scan each of these for an OS or one or more OSs. It's a lazy algorithm, so maybe the first thing you find is what you boot and you didn't even bother checking the others. Obviously, checking USB is very slow. But if you want to see them all, then that's what you do. And then you end up with this list over here, which you can present to the user in some sort of menu format and show, what do you want to boot. So that's just of course, in some cases you may not let the user choose. If it's an embedded system, probably you're just booting whatever you say you want to boot. But you may still have other options, different options. So I'll just talk about what I'm calling VBE OS requests. So these are things that the operating system requests. I would request a martini, actually. That would be excellent. So what is an OS request? Essentially, it's the operating system saying to the bootloader, please give me this. I need this to boot. Or it would be better if you did, because things will be better if you give me the stuff that I'm requesting. And I'm just going to use one example just to keep it simple. Here we have Linux requesting some random numbers. And the way that works is we put this request actually in the metadata here. And we say, okay, here's some random numbers. This is the driver effective. It's going to produce this information. Sorry for those of you who have never seen a device tree in your lives, but I guess it's pretty common on Linux, so hopefully you have. And this is the size and so on, and it's actually required. We have to have it, or you cannot boot me. Okay, so that's the request, and here's the response down here, where we say, okay, here's the data, here's the random data you asked for. So that's how it works in VBE. And just for comparison, I want to talk about how it works in UEFI protocol. So essentially, the way it works there is U-boot just jumps into the abyss. Doesn't know what it's booting, doesn't know what's happening, but it loaded something, so it's going to jump to it. At the other end of that is an EFI stub or grub or whatever it might be. It then, if it's the EFI stub, it then calls back into U-boot. Effectively calls back and says, okay, give me some random numbers. It might call in to read the RAM disk. It might call in to do a lot of different things, right? And essentially, this process goes on. The stub builds up the state, and then once it's built up that state, it then jumps into Linux. It updates the device tree that's passed in with this information, mostly. Some of it just stuffs in a configuration table list in the EFI, and then requests it again on the Linux side. So it's the reason I had that complicated machinery cartoon a few slides back was because I think this is over-engineered. How it works with VBE is that we can see the requests that the OS has. We process them all here. We boot with the device tree with all that stuff in it, and Linux just starts up and runs. So that's the difference. Oh, you can, and when I finish, because I do want to get through. But I'll give you can be the first question. So so that's the difference. Now here's where I think the advantages are. There's no callbacks. There's no double handling. We don't need the EFI stub at all. It's also deterministic because I can tell you by looking at the requests that are published in that metadata, I can tell you what you need and whether it's going to work or not. It's an awful lot less code. And I think it's easier to test. And I'll just mention some of the request types that I discovered in Linux 6. This is an eye chart, which I just had my eyes tested recently, actually. So I know what an eye chart is. I think I failed because I need glasses. Anyway, so there's quite a lot of things. There's about, I think, 12 things that are going on in that EFI stub. And that's essentially the sort of things that we're talking about creating these OS requests. So how do you enable EFI, or sorry, gosh, what a funny slip. How do you enable VBE on a board? So the way it works is you just create this node in your device tree. You say, this is my, I want to use VBE simple, which is just a very simple single firmware thing. And you give it some parameters, and you're done, essentially. On the OS side, what happens is U-boot actually stuffs this into the chosen node so that Linux can see, okay, you're using this boot method. And then when firmware update D starts up and runs, it looks at this information and goes, okay, I know all the parameters. I'm just going to update the firmware as needed. So it's sort of all integrated in that way. And of course, VBE simple is just a demo. What we really want is this A/B recovery business where you can essentially, have multiple images to avoid bricking and to provide a recovery flow and so on. So that's something that's yet to be done. But again, it uses VPL to make that decision. And then when it does, it goes down one of these three paths here. Each of them, you'll notice, has complete copies, independent copies of all of these binaries. So recovery typically is read-only. So when you ship it, that's what you're always going to get. A and B can update as needed. You update the B and then boot from it to see if it works. If it doesn't, you fall back to A, that kind of thing. So that's what that's about. If you've got a TPM, you can do rollback protection, and that's what the vernum field is for. It effectively is just a monotonically incrementing version number. I mean, there's a version string as well, but that's not super useful for the TPM. And when you do an update, you can specify a minimum rollback so that it can't go back too far. Obviously, TPM can be used for this remote attestation stuff. That's not really a function of the firmware, but it has to have, has to set the TPM up for that. I'll just mention a few things related to VBE. So if you're interested, I'm not going to talk about them, but just if you're interested, you can follow the links. So there's U-boot standard boot, which I mentioned. It's just really a way of getting rid of the distro boot scripts and having it all sort of handled automatically. There's a thing called the firmware handoff protocol, which has been going back and forth for a year or so now. That is essentially a way to pass information between the firmware stages. And in particular, very early on in firmware, you have very little memory and so on. So it's a very small, compact, for very simple things like, okay, here's how much RAM you have or something like that. So that firmware boot protocol, handoff protocol is underway, and there's a proposal from ARM about how that should look. There's distro boot that I mentioned. There's the firmware update D plugin, which only supports VBE simple at the moment, but there's some documentation associated with that. And then there's various documents, I think it's 4 or 5 or so, linked from the documentation, from the U-boot documentation, and the OS requests hasn't found it in there. So these are all links if you want to find out more about it and how it actually works. So, I'm getting to the end of my pitch. Here are some of the objections you might have. And essentially, my answer to each. So, I claim that U-boot's an industry standard. I don't know what else we could call it. It's been around for a long time, at least on some architectures. Well, VBE does not have a specification today. It will. And I think it can fill that same sort of gap. I hear a lot that we can't ship the kernel and device tree in a FIT. We want them in separate files. Okay, fine, doesn't matter. We do need the metadata though. So maybe that's a separate package. What about ACPI? Yeah. Honestly, that's another whole other talk. But yeah, if you want to use ACPI, there's no reason why you can't. The U-boot does support it on x86 and actually on ARM. And what about grub configurations and the ability to, put the CFG files and so on? Well, okay, that's not there. So run grub if you have to. And this is another question that I have not looked at in any detail, but it seems to me we could do better there. It seems to me that we could make it a bit more deterministic how things actually boot with logos and so on. So what state are we with VBE? Where is it? Well, it's taken a lot longer to do than I thought it would. I'll say that. I think for about 6 months or so, it was hung up on the idea of, well, we've got UEFI, why do we need anything else? Please don't do anything else. We're using UEFI. And so, as I say, when I came from it from the point of view of, well, we're not doing that, so what else would we do? Then, there were some difficult discussions. But anyway, most of the major design is in pretty much the final stages. There's quite a bit of support in this for U-boot. The OS request thing has been posted. And while U-boot has VPL, it's empty, so that needs to be done as well. So essentially what we have is the beginnings of it, but there's still more to go. And the end-to-end demo that I was hoping to bring, I had a little bit of challenges in my life in the last month, so I haven't got as far as I hoped with that, but that'll come along soon. So you've either been repelled or attracted by this. I don't know, where you are with it, but if you're attracted to it and you want to get involved, here are some ideas. It's obviously very much still in progress. There's a lot of major ideas there, but there's still some details, as you can see. And yeah, if you're all interested in this, please give it a try. Just say no to UEFI. Thank you.
Thank you, Simon. And I guess you have a question, right?
Thanks, Simon. I'm a VM5 maintainer in U-boot. So there's, I don't have any real objections, right? My point of view is different. My point of view is that this is fine for smaller devices, but the idea for EFI is that you can boot different OSs, right? You can boot OpenBSD, you can even boot Windows if you have ACPI support properly plugged in, right? Most of the things you discussed are already there. So AB updates, they're getting merged, and we have, the OS playing a role in the updates in U-boot, and you can confirm the firmware or not as an OS. some of the things that are on paper look good on paper, but that's not, so the callbacks that we have to do from the stub to the EFI are a necessity. It's not something we designed because we thought it's easier, right? So for the initramfs specifically, right? You need the bootloader to be aware of the OS memory mapping, which is insane as an idea, to load it from the bootloader. And keep in mind that in the kernel, we change the memory mapping all the time. So you have to have the bootloader being aware of intrinsics and internals of the OS, which makes no sense. What UEFI does, and the stub is, once the kernel is up, it calls the EFI and it says, here's a memory, copy the initramfs there for me. And that's never going to change. That's a stable ABI we're never going to change. While on the other hand, if you have to allocate memory from the bootloader and place the initramfs, you have to know memory mapping rules of the OS itself, which doesn't scale because the kernel will just change the memory mapping on the next release and you'll have incompatibilities. So most of the callbacks we have are not a design decision. It's a necessity to have a stable ABI and not have to change it over versions, right? And on top of that, I've heard people saying, yeah, UEFI is insecure. We have to have runtime services. You don't have to have runtime services. No one tells you need to have runtime. You can disable them, right? So all the things that the stub does, and there's stuff like TPM, the event logs, all of this in the kernel are heavily plugged into EFI. You can't use the TPM if you don't boot with the stub. You can't get you can randomize the kernel for KSLR, but you only randomize a portion of it if you don't boot with EFI. So there's things that are plugged into the OS at the moment that you will have to heavily change, will have to have different entry points into the kernel. And it's not only the Linux kernel, right? You have to do the same thing in BSD, FreeBSD, OpenBSD. So EFI just gives you a useful abstraction to boot whatever you want.
So
right?
I think we're up to at least 3 beers worth of discussion already. But I think it is a bit of a hard thing to get across. But essentially, the way the requests work. Firstly, I'll say that the current UEFI implementation does not let you update much. Basically, the updates are there isn't a proper concept of the read-only versus the read-write side. That needs to be figured out with EFI. But with respect to the requests, there's nothing to say that the kernel can't publish in that metadata, okay, here's where I want things to go. And that can be implemented. And well, this is two ways. Having the kernel publish that information statically because it knows what it's doing at build time, or saying, I have no idea, but at runtime I'll figure it out and let you know. That's the two models. I'm saying we can do it statically. We can then say there's a certain amount of here are the rules. Here are the rules, and program the rules into the protocol and standardize that, right? Because Linux is not doing random things; it's doing it based on some objective that it has. So anyway, as I say, we have a lot of discussion to have about all of this, but yeah, we'll keep at it. Anyone else have anything?
You first.
Oh, this should be quick. One of the pain points with exit boot services comes up when you do a kexec. And I'm wondering, have you looked at, I mean, this looks neat. I'm just saying that, but how does this interact or play with when you do a kexec? Have you looked at that?
Well, essentially, exit boot services is not running, and we don't even run the stub. So you literally jump straight into Linux. So there's no exit boot services. You have to provide those as well, and then pass them through. Yeah, the metadata would say, I'm going to be running another kernel, and I need some data for that. Something along those lines, yeah.
Hello, I'm Vincent, working at ARM on System Ready. So first of all, I want to say thank you for this VBE presentation. So in general, ARM welcomes innovation. So it's very interesting, thanks. On the System Ready program, we have settled on the UEFI interface across the board, as Elias mentioned. So it allows us to boot, and our partners to boot on the high-end servers and down to the smaller IoT type of devices. And sometimes with the same binary image or ISO installer image. So it's happening today. I just wanted to say, you make UEFI sound like it's overly complex. So that was my impression at the beginning as well. But for the smaller type of devices on system ready, we have this EBBR specification, which was largely the work of Grant Likely and the community. And it's something like 25 pages only, which we need to boot on those smaller type of devices. And I think we are achieving most of the goals that you have described with VBE. And so I hope in the future we can benefit from each other.
Sure, thank you. I'm not sure if there's a question in there, but I'll just respond that, you know, I do understand that ARM has certainly been pushing UEFI, pushing ACPI, and pushing essentially what I consider to be x86 legacy things. I think, with respect, I think it's a great shame because I think ARM has had the opportunity to do things from scratch, and particularly initially the push has been, you know, very much to go with this, you know, follow along Intel footsteps, even to the extent of having different blobs and so on in the firmware. So I wish and hope that we can turn that around, honestly. Maybe not in the server space, but at least for embedded devices.
Thank you. Okay, last question.
I have a quick question on the, so if we go back to a previous slide, there is a diagram between EFI and VBE. And I know that EFI step would delete the memory nodes from the FDT. And I'm wondering for the case of VBE, do you guys mess around with the memory nodes in the device tree? Or users can, in a Linux boot up from VBE, can you safely assume you can pass memory map from the flattened device tree?
Well, there's nothing in the way between you and Linux. So yeah, you can pass whatever you want Linux to see. If there's a need to make some changes, then you know, that would need to be encoded in the policy that, you know, for each particular request. For example, you might have another request that says do this to the memory nodes or something like that.
So that's to say by default, say VBE simple, remember it correctly, and then the memory nodes, reserve ranges, and all that will just show up in the device tree.
Exactly.
Okay. Thank you.
Yeah.
All right.
All right. Thank you. Sorry, I have to talk to you afterwards. Sorry, I couldn't get time. There's obviously a lot of things going on here, and it's pretty early days. But thank you very much for listening.
Thank you, Simon.